Now let's look at the final two transformations that we're going to look at in this chapter. And those would be vertical stretching and shrinking and horizontal stretching and shrinking. One practical example that might illustrate these concepts are when we're using our cell phones and looking at things on the screen, and we may use our fingers to zoom in and then zoom back out on the screen and change the appearance of what we're looking at on our phones. That's a really great example of vertical stretching and shrinking and horizontal stretching and shrinking. Of course, your phone is working with a digital image and manipulating the image that you see on the screen, but that's a really good connection with our mathematical material here with vertical and horizontal stretching and shrinking. Now, for our purposes, we're really going to focus just on the vertical stretching and shrinking. I will show you an example with horizontal stretching and shrinking, but we will really focus on just the vertical. Now, you'll see the form here for vertical, y equals c times f of x. Notice again that value c is outside the argument of the function. That's how you know it's vertical. If you look at horizontal, now you see c is inside the argument of the function. Now, what we're really doing is multiplying the function by some value c. There's two cases. If c is greater than 1, that's a vertical stretch. In other words, if I multiply some numerical value by a value bigger than 1, it's going to get larger. Then there's another case where c is a fractional value. If I multiply a value by a fraction, it will get smaller. That's what we call vertical shrink. But essentially, our manipulation, because we're working with a vertical transformation, we're going to multiply our y coordinates by c. Now, I will show you an example of horizontal, but notice with the horizontal transformation, we're going to work with the x coordinates, but it's going to be the opposite of multiplication. There are two cases where c is greater than 1. That's really a horizontal shrink. And if c is fractional, when we divide those x coordinates, that will actually have the effect of stretching the graph. So just notice between vertical and horizontal, all right, of course, vertical we work with y, horizontal we work with x, but notice the operations are actually opposite. Vertical is a multiplication, horizontal is division. On page 289 of your textbook, you'll see this nice summary of the vertical stretch and shrink of graphs. And again, just keep in mind we have a couple cases. When that value c is greater than 1, it's going to be a stretch. So you can see the original curve is the blue line, and then of course those y values become larger and the curve gets stretched out. But if c is some fractional value, notice now the blue curve has been shrunk as the y values get smaller. So again, we can just, before we ever really graph a vertical transformation, we can know whether it's a stretch or a shrink based on that value of c. So let's look at example 6. Use the graph of f of x equals x cubed to obtain the graph of h of x equals 1/2 x cubed. In example 6, we have our base function f of x equals x cubed, the cube function, and the transform function is h of x equals 1/2 x cubed. Now I can identify here that value c is 1/2, and because that's a fractional value, this will be a vertical shrink. Again, if c had been greater than 1, I knew it would be a vertical stretch. But I will identify that transformation. This is a vertical shrink. And I will multiply the y coordinates by 1/2. So again, let's come up with our table of coordinates for the base function. And here I can use those typical x values from -2 to 2. And so right, -2 cubed would be -8. This will be -1, 0, 1, and 8. And then we can just apply our transformation. So this would be x and h of x. Now, with this transformation, we're only changing the y coordinates. So again, I can just copy the x coordinates over. And then it's going to be the y coordinates that will multiply by 1/2, or the same thing as dividing by 2. So this would be -4, right? -1/2, 0, 1/2, and 4. So looking at the graphs of the textbook, this is the original cubic function, and you'll see the points there, just as you see the points in our table here. And then this is the transform function, and again, we were able to calculate those points without graphing. Right? You'll see there's the point -2, -4, 2, 4, and these are those fractional values, right? 1.5. If you look very closely, -1, -1/2. But there is our transformed function with the vertical shrink. In order to get a little extra practice, I'd like everyone to do checkpoint 6 here that you'll see at the top of page 290. So I'll just write that in our file here quickly. As I mentioned earlier, I'm not going to stress horizontal stretching and shrinking for our purposes in this class, but I do like to show you all the possible transformations just to be complete. As I mentioned before, with horizontal stretching and shrinking, again, you'll notice the value c will be inside the argument of the function. That's how we know it's horizontal. And instead of multiplying y coordinates by that value c, we're going to divide the x coordinates by c. So when you're dividing by a value larger than 1, the values get smaller. That's why we have the shrinking effect. However, when you divide by fractional values, that will actually increase the value of that divided quantity, and that has the effect of a stretch. So let me just step through example 7 to show you how that transformation works. Example 7, you'll see on page 290, will have two parts to it. In the first part, c is greater than 1. This will actually be a horizontal shrink. And then in part B, it's 1/2. It'll actually have the effect of a horizontal stretch. Now, one important reason I also want to show everyone this problem is we haven't seen this up to this point. All our transformation problems so far have worked with one of our common algebra functions or base functions that we would be familiar with. However, you can also see problems where the function is defined in another way. In other words, this is not a standard or common function that we saw earlier in the chapter. But we do have 5 coordinate points it's defined that we will work with in order to solve the problem. So if you're given a problem like this, carefully identify 5 points from its graph to create your table of coordinates to complete the problem. So in order for me to get this problem started using our tabular method, I'm going to use these 5 points that you see listed in the textbook to get started. So in example 7, again, we have 2 parts to the problem. Part A is graph g of x as f of 2 times x. Again, that value of c or 2 is inside the argument of the function, and because it's greater than 1, this will be a horizontal shrink. So when we set up part A of the problem, we'll have one transformation, and it's going to be a horizontal shrink, and we will divide the x coordinates by 2. So using the 5 points that we see in figure 2.52 on page 290, these are those 5 coordinate pair points that I want to work with, and now we'll apply the transformation. So here again we'll have x and g of x. Now again, we're not going to change the y coordinates, so I can just copy those over. And now let's divide the x values by 2. So this would be -2, -1, 0, 1, and 2. So when you look at the solution of the textbook, there's our original function f of x, which you see I created the table of coordinates with the 5 coordinate points. Then we apply the transformation, and there are the points that we identified in our table. -2, 0, -1, 4, 0, 0, 1, -2, and 2, 0. Now in part B, we're going to have a horizontal stretch. And what we will do is divide the x-coordinates by 1/2. Now remember, division really turns into multiplication of the reciprocal of what you're dividing by. So you can also think of this as the same as multiplying by 2. That may be the easier way to look at this manipulation. So again, here are our 5 coordinate points given to us from the graph in the text of f of x, and we'll apply the transformation. So we'll have, this is x, and I believe this is now h of x. As we saw in part A, we're not changing the y values, so I'll just copy them over. 0, 4, 0, minus 2, and 0. And now we're going to divide the x values by 1/2, but it's really the same as multiplying by 2, which is probably a little bit faster to do. So minus 8, minus 4, 0, 4, and 8. Looking at the solution in the graphs in the textbook for part B, again, there's our original starting function, and those are the 5 coordinate points we worked with here. And after applying the horizontal stretch, again, you can see all the points that we determined with our table you'll see in the graph. Minus 8, 0, minus 4, 4, 0, 0, 4, minus 2, and 8, 0. And you can see the graph has been stretched out horizontally.